So now we come to the new topic, that is the basic amino acids. So in basic amino acids, we know that NH2 groups are greater in number than the COH group, and therefore when protonation occurs, it leads to the formation of H plus being added on both the NH2 sides, and thus a development of dication occurs. Okay. So next what happens is that we have to lose an H plus to find the Ka, that is a dissociation constant. So H plus is lost from this particular side, that is the COOH group loses an H plus and converts this into a cation. So we have got a cation over here. Next, the only H plus which can be lost from is from this NH3. Okay. And when this NH3 loses, then what happens is that the positive and the negative charges are equal in number, as can be seen over here and here, and thus get a dipolar ion being formed. So this is a dipolar ion. Okay. Now next what happens is then when further H plus is lost, then only there is NH3 positive which can lose the H plus, and therefore the last species that develops is the anion, because there is a excess of negative charge. So we have moved from a dication to an further a positive charge being removed, that is the cation, and moving on to the dipolar ion can be represented by Di, and next we have an anion. So we have this particular series that is taking place. So we have got Ka1 being involved over here, then Ka2, and we have got Ka3. So we have got three dissociation constant. Now, if we represent it on a pH scale, what happens is that it can be divided into two parts, and the first part, the pH will be calculated by averaging the pKa1 plus the pKa2. The second pH will be found out by half of pKa2 and pKa3. Now, so we know that at the beginning we had the dication in a larger amount. So dication is in larger amount over here, followed by a cation being in large amount in the midsection of this pH scale, followed by an anion at the end of the scale. So if we have to find the isoelectric point, we know that the isoelectric point is in midway, where the cation and anion have equal number of charges or equal number of concentration, and therefore this particular part will give us the Pi, that is the isoelectric point. So this is for the basic amino acids that can be seen, and if we saw that the more number of NH2 groups are involved, then we take the dissociation constant of the last two, that is Ka2 and Ka3. But if we have more number of COOH group involved, then we take the first two Ka average, that is the first two dissociation constant average. Now, moving on to the next part, we have some amino acids over here, and we have to learn the names so that we keep them in mind. So the first one, that is the basic one, is the glycine, and it is represented by GALY. Moving on, we have an addition of CH3 group over here, and when this gets added, we call it alanine, and it is represented by ALA. Now, the next one that we have has an addition, more additions to it, and therefore this is known as valine, represented by VAL. The next one that we can see, which has a longer group, longer chain involved now, and this is known as leucine, represented by LEU. Moving on to the right hand side, we have over here the name of this one is isoleucine. It is similar to leucine, but we have got a different group attached over here, and it is represented as ILE. So these are some of the amino acids that can be remembered by GAVLI. So this is G stands for glycine, alanine, valine, leucine, and isoleucine. So now, keeping these amino acids in mind, we next move on to the peptide linkage. Now, what is a peptide linkage? So let us take for instance that we have Over here we have glycine, and on the right hand side we have got alanine. So when we remove an OH group from glycine and we remove an H group from alanine, that is, we remove a water molecule, then we get a new compound being formed, and that can be represented by NH2, CH2, C double bond O. Now we have lost that OH, and in place now this is connected to NH of alanine, and we have got CH, CH3, along with C double bond O and OH. Now this over here is known as, we call this a peptide, and this particular bond, this is called the secondary amide linkage. Now which is the secondary amide linkage? This particular linkage is called a secondary amide linkage. Now this is known as a diapeptide. This is called a diapeptide, and diapeptide because it was formed by the two monomers that we took at the beginning, that is the glycine and alanine. So two monomers when are involved, they lead to the formation of diapeptide. And please remember that diapeptide have only one peptide linkage. So two monomers are involved, but there is only one peptide linkage. So the number of monomer involved, so the number of peptide linkage will be one less than the number of monomers involved. Next, if we see an example, that is, we have been given two amino acid. Now G represents the glycine and A represents alanine, and we have to write how many dipeptides can be formed. Now dipeptides can be formed by repetition. So we have, suppose we took take two glycines, or we took, then also it can lead to the formation of, we can form dipeptides over here because you have to take two monomers. Also, what if we mix them? That is, we have got alanine and then glycine, and then we have glycine, then alanine. Now, what we have to keep in mind over here, that this alanine glycine has a different structure than glycine and alanine. So if glycine glycine comes first and then alanine comes, then the structure looks something like this. That is, first we have glycine, which is attached to alanine. So we have got ourselves a structure like this. But if we have alanine first and then glycine, then the structure looks a little different because alanine comes first now. And when alanine comes first, the structure will look something like this. So alanine will be the first one, and then we have C double bond O. OH is being lost, connected to an NH bond which has lost NH2, CH2, C double bond O, and then OH. So these two will look different. Therefore, we'll say that how many dipeptides can be formed? So four can be formed when repetition is allowed. If we see the next question over here, we've been given three monomers, that is glycine, alanine, and valine, and we have to form dipeptides with them, but there should be no repetition. So no repetition is allowed. Therefore, we cannot have three of the same type. So when this is the condition, then first what we can do is that we can have GA, then we can have AV, then we can have, or we can, what we can do is, if we are writing GA, then we can write just the opposite, AG. If we have AV, then we can write VA. If we have GV, then we can write VG. So we have got all the dipeptides, so we can call them fourth, the fifth, and the sixth. And there is no repetition over here, so we can just say that these have six combinations. That is, six dipeptides can be formed. Now, moving on, if we see that there is another simple formula for calculating these dipeptides, and that is that 3C2. Now, 3 is the number of monomers that is given to us, which you can see that it is GAV. 2 is the number of types, that is 2 is the dipeptide. So 2, we we take a 2 over here, and since it can combine in two different ways, then we have it multiplied by 2. So if we calculate this also, it comes out to be 6, and therefore we can calculate the dipeptides by this way. But this particular method is the more viable one. So we should do it by this method. Now next we have AGV, and we have to calculate the number of tripeptides. So we have tripeptides over here, and there should be no repetition. And when this condition is given to us, so what we do is we apply the same method. So let us start by writing AGV. Now keeping the A similar, let us just switch V and G. Next we can take G, can have AV, and we can keep G constant and we can call VA. Then we can have V at the front, and then we can have GA, V at the front, and we can have AG. So these are all the monomers combination that we can see, and we can see that there are 6 combinations, and therefore we can have 6 tripeptides which can be formed with these given monomers. Okay, now we should keep one thing in mind, that if there are tripeptides, then we need 3 monomers. So if tripeptides are the ones which are being formed, then tripeptides are in need of 3 monomers. Then we need 3 monomers, but the number of peptide linkages will be one less than the monomer, so there will be 2 peptide linkages. This thing we have to keep in mind. So what if there are tetrapeptide? Then we'll have 3 peptide linkages, but we'll have 4 monomers. Okay, so that is the thing that we have to keep in mind. Now coming on to the last question that we have, that is, what if we get AVGL and we are asked that how many tetrapeptides can be formed which do not, you have to keep in mind that they do not start with A and end with L. Okay, so we have to keep this in mind, that they don't have to start with A and end with an L. So let us just start writing. So we have got A at the front, then we can have VGL as it is given in the question. We can have AV being constant and LG switching their places. We can have AG and then VL. So we are switching the places of everyone. So AG, LV, then we can have AL coming to the front, then VG, then we can have AL again, but now we switch the places of GV. So we have got these 6. Now if we do it by everything, so let us just say that we do the same method for V, and we do the same method for G and L. So of course we'll get 6 from each, and therefore we'll have 6 into 4. So there are 4. So we can have 24 combinations. So total possibilities are 24. In this manner, we can just say that the total possibilities, if we continue like this, so the total possibilities will be 24. Now, if we see those ones which end with L, so we'll have, suppose these are the A ones. Now the ones which end with L, so let us keep L as a constant and we move these 3. So we can have AGV, then we can have GAVL, LGVAL, then we can have L, we can have V at the front, and then we can have VAG, then we can have an L at the end, and we can have VGA. So these are from V at the front, these are from G at the front, these are from A at the front. So we were looking out for peptides that end with an L. So now we know that these 6 will end with an L. So we have 6 combinations which end with an L, and we have 6 combinations which start with an A. So out of these 24, we'll subtract 6 for starting with A, and we'll subtract 6 for ending with L. But we can see over here that we have subtracted these particular and this particular one twice. So we can now just add 2 because we have subtracted 2 of them twice. And now if we calculate, we can have total number of tetrapeptides as 14 tetrapeptides. Okay. So this is how you find the answer. Please don't naturally use the combination method. Instead, you write it for yourselves and see which one has to be taken and which one has not to be taken so that it makes the job easier. Okay. So now we can see that when we do all this, we get a total number of 14 tetrapeptides. We do not start with the A and end with an L. So that brings us to the end of biomolecule.